In this hour, we will introduce the very important object or tool for LTI circuits, namely the transfer function. And in fact, this tool is not useful only for LTI circuits, but for LTI systems in general. But of course, we will be looking at the thing from the circuit point of view. The definition is very simple and intuitive. So let's first define it, and then we will work out the consequences of our definition. Okay, for an LTI circuit, the transfer function usually denoted by G or H of S from some input, which we denote by W, to some branch current or voltage, or output, which we denote by Y, is the ratio of a zero state response transform Y of S to the excitation transform, to the input or excitation transform. W of S. Okay, note that here we use the article A, so it doesn't really matter with which kind of input you're exciting the circuit. Okay, the assumption is that the circuit has a single input, or you may have more than one input, but you kill all the irrelevant ones and you set all the initial conditions to 0. Okay, you excite the circuit with some input signal, and then you go and record the, let's say, the output, the response, and then the ratio of the transforms Y of S to W of S is what we're defining as the transfer function of the circuit for the given pair of input and output. Okay, so here is a simple picture describing the situation. Here, this box, this block is representing, suppose, our circuit. Okay, LTI circuit. And the assumption is that it's a single input circuit, and we set all the initial conditions to 0. Okay. And this circuit is driven by our input W, and that input produces an output Y. Okay, and then for this situation, the transfer function for this circuit, for the given input and output, okay, is simply Y of S over W of S. Okay, if for example, W is the current of an independent current source, if that's our input, and if the output that we're interested in is the voltage that appears across the terminals of our input, then the transfer function would simply be the impedance seen by the independent current source. Okay, so in a sense, transfer function is a generalization of the concept of impedance. Okay, so this clearly implies that Y of S equals H of S times W of S. Okay, and this equation makes it clear that if you have the transfer function of your circuit, then whenever you apply a new input to the circuit, you don't have to solve the circuit from scratch once again. If you have the transfer function to figure out the output, all you have to do is compute this product, H of S times the transform of your input, and then take the inverse Laplace transform, and that produces Y of T, the response due to your input, okay, under the zero initial conditions assumption. Okay, let's apply this definition to a simple first order circuit. Suppose this is our circuit, okay, where input is the voltage provided by the voltage source. This is W, R, C, and the output is collected from as the voltage that appears across the terminals of our capacitor. To obtain the transfer function, let's transform the circuit to S domain, which is easier than usual because since we're dealing with the transfer function, or we're studying transfer function, by assumption all the initial conditions are zero, therefore our dynamic components will be represented only by their impedances because all the initial conditions are zero. So that means this circuit produces the following S domain equivalent. Okay, 1 over SC, the impedance of our capacitor. This is R. Here we have W of S, and this output is, this voltage is our output, Y of S. And Y of S can be related to the input simply through voltage division, and that will give us immediately the transfer function. Okay, H of S is Y of S over W of S, okay, by definition, and that equals 1 over SC, okay, the impedance of the capacitor divided by the overall impedance seen by the voltage source, which is R plus 1 over SC, R plus 1 over SC, which reads 1 over RC over S plus 1 over RC. Okay, so that's the transfer function for that first order circuit. Now, let's talk about poles of the transfer function and the output. Okay, the poles of the output, Y of S, okay, come from either the transfer function H of S or the input signal W of S. Okay, this is clear from this expression, Y of S equals H of S times W of S. Okay, so the poles of Y of S should either come from H or W. Now, for the special case when there are no repeated poles, okay, Y of S can be written as sum of two separate summations, and in the first piece we have the poles associated to the transfer function. In the second piece we have the poles associated to or coming from the input. Okay, so namely Y of S can be written as J Kj over S minus Pj. Okay, so these are the poles of the transfer function, let's say, plus Li S minus Qi. And we have the second sum of terms, and they're representing the poles of, or they're coming from the poles of the input W of S. Okay, P J, the poles of the transfer function, and Qi, the poles of W of S. Okay, and remember what a pole was. Note that we're talking about rational functions, some polynomial of S dividing some other polynomial of S, and the poles by definition is the roots of the denominator polynomial, and the roots of the numerator polynomial we called the zeros of our transform of our signal. Now, since h of s is independent of w of s, okay, so it's directly related to circuit, the poles of h of s, provided that the order of the transfer function and order of the circuit are the same, are no other than the natural frequencies of the circuit. Okay, so poles of h of s equals natural frequencies of the circuit, under the assumption that h of s and the circuit is of the same order. It may be that in certain cases the order of h of s is strictly less than the order of the circuit, so that means some of the natural frequencies cannot be observed from the transfer function. Okay, so if you want to be precise, then we have to replace this equality sign with the subset notation. Okay, but if the orders are the same, then we don't have to worry about that. Okay, for y of s written in this form, we can easily write down the form of y of t. Let's do that. Okay, then we can write y of t as Laplace, inverse Laplace transform of that summation plus inverse Laplace transform of that summation. In other words, we have j kj e to the pjt plus I li e to the qit. Now, since these terms are related to the natural frequencies or coming from natural frequencies, this is no other than the homogeneous solution piece, and then these terms e to the qits, they're coming from the input. Okay, they're coming from the poles of the input. Therefore, this piece is our particular solution. Okay, so let's revisit our example under this observation. So suppose we excite our circuit with a sinusoidal signal. So Rw is cosine omega t, Rc, and here we have y of t. Okay, the output that's generated when the circuit is excited by cosine omega t, and initially the circuit is at rest. Okay, so no initial capacitor voltage. So this case produces the following: y of s equals, okay, so the transfer function is here, y of s equals the transfer function h of s times the transform of the input. The transfer function is 1 over RCS plus 1 over RC times the transform of Laplace transform of cosine omega t, which we know equals s over s squared plus omega square. Okay, so this is our h of s, and this is our w of s, because this thing is our w of t. Okay, the input. And then the poles of y of s for this situation are such that it has a pole at minus 1 over RC, and it has a complex conjugate pair of poles at plus minus j omega. And the first pole produces the homogeneous solution k1 e to the minus t over RC, and the second pair produces the particular solution. Okay, L1 e to the j omega t plus L2 e to the minus j omega t, where L1 and L2 must be complex conjugates of one another. So this is the homogeneous solution, and this is the particular solution, where L2 is L1's complex conjugate. Okay, now let's talk about the transfer functions of one-port circuits, and then we will generalize that to the two-port case. Okay. The transfer functions of one port and two port circuits. Okay. There isn't really much to say about the one port because it's very simple. We have a single port, so that means we have a single input and a single. Well, we have just a current, the input current and input voltage. Therefore, their ratio will be our transfer function. Okay. This is the one port case, and I of s plus minus v of s. Okay. Now, if you take the input as the current and the output as the voltage, then their ratio v over I is the transfer function, and v over I is also previously defined as the impedance. Therefore, the driving point impedance, or the input impedance, or simply the impedance of one port is that special transfer function, the ratio of the voltage to the input current. Okay, so driving point impedance, okay, or sometimes just simply the impedance, is a special case for a transfer function. Okay, so z of s, okay, sometimes we use this notation, z of s equals v of s over I of s, which we treat as the input in this case. Clearly, you can also talk about the driving point admittance. In that case, the current appears in the numerator and voltage in the denominator. That means, for that case, we're treating voltage as the input and the current as the generated output. Okay, so this is all we can say about one port. It's not really interesting, but let's also talk about the two port case where we have many possibilities. Okay, so let's put it here. Okay, now for the two port case, there are a number of possibilities. Okay, plus minus V1. So for simplicity, let's always put the input to the left hand side and collect the output from the right hand side. So if this is the voltage is the input and the output is the voltage at the other port left as open circuit. Okay, so this is the input and this is the output. Okay, for that case, HV of S is simply V2 of S over V1 of S, output divided by the input V1 of S. Okay, V2 of S over V1 of S. So this is called the voltage transfer function. Okay, and then we can talk about the dual case where we have input entering from the first port, and then the second port is shorted, and I2, the current flowing through that wire, is our output. Okay, and then we have the transfer function as I2 over I1, and that's called the current transfer function for the through port. I2 of S over I1 of S. So this is called the current, the transfer function for the one port. And then we have the mixed situations. So such as plus minus V1. Then here we have I2. And then we have Hy of S equals the output divided by the input, I2 of S over V1 of S. So we're dividing current by voltage, so therefore we're talking about some sort of admittance, and therefore this is called the transfer admittance. Okay, and the dual of this will produce the transfer impedance, where we have current source here and we collect the voltage from the second port. Let's also put it on the board. Plus minus V2, that's our output, and here this is our input I1, and Hz of S is simply V2 of S over I1 of S, and this is called, since we're taking ratio of voltage to current, so we're talking about some sort of an impedance, or at least units is ohms, therefore this is called the transfer impedance. Okay. Transfer impedance. Okay. Now, so far, when we talked about a transfer function, okay, yes. So it's the ratio of some scalar signal to some other scalar signal in S domain. Now, clearly, so that means we have a single input and a single output. Clearly, that can be generalized to the case where we have input more than one input and then more than one output. In that case, the input will be represented by some current, some vector, and likewise output in general would be represented by some other vector. And then the transfer function would be an object that relates one vector to another vector. Okay, so when we're trying to describe the relation between two vectors, matrices appear automatically. So the generalization would be the transfer function matrix. Okay. Now we will not talk about the entire, talk about transfer function matrices in its entire generality, but it would be nice to mention some simple, useful examples to that. Okay, so for instance, one can talk about impedance parameters. Impedance parameters, okay? So what we're doing here is we're generalizing the concept of resistance matrix that we talked about in 201 for LTI resistive circuits, okay? Generalization of that resistance matrix is the impedance matrix for LTI dynamic circuits. So here is a simple example. Okay, suppose this is our two-port plus minus V1 plus minus V2 1 over SC, SL, and R. Okay, now we're going to treat the current as the inputs and the voltages at the port terminals as the outputs, and then we will try to figure out the relation between the outputs, okay, V1, V2, those voltages, and the inputs, I1, I2, the currents. And if you do that, what happens is an impedance matrix appears, okay? So obtain the impedance matrix or impedance parameters. So clearly what we will have is, here we have the output, okay, and then here we have the input, I1, I2, and it's a vector of size 2, and input is also a vector of size 2, therefore their relation should be described by a 2 by 2 matrix, and that 2 by 2 matrix is what we're calling the impedance matrix, or the impedance, or the entries of the impedance matrix are called impedance parameters. Okay, so we would have Z11 of S, Z12 of S, Z21 of S, and here we have Z22 of S. Okay, clearly we can also talk about admittance parameters, the hybrid parameters or chain parameters for 2 ports in S domain. So that all of them will be matrix generalization of the concept of transfer function, which we defined initially for the single input, single output case. Okay, let's obtain the impedance parameters, and then we can move on to some other examples. Okay, here is the solution. So we can write easily this voltage as this voltage plus minus plus the voltage drop across the terminals of the resistor. This voltage is I1 times the impedance of the capacitor. Okay, so 1 over SC I1 plus R times the current passing through our resistor. So I1 is coming from here, I2 is coming from here, therefore the current passing through your resistor is I1 plus I2. I1 plus I2. Okay, and this equation will immediately give us the first row in our transfer function matrix, or the impedance matrix. And we have, okay, so let's reorganize that. R plus 1 over SC times I1 plus R I2. As for the second voltage, we have SL times I2 plus, again, the same voltage, okay, over the resistor. That produces R plus SL. Okay, so let's write I1 first. That produces R I1 plus R plus SL times I2. Okay, and then we have immediately all the entries, Z11, Z12, Z21 and Z22. So that means our impedance matrix. Okay, so this is our impedance matrix, Z of S, for this case equals RCS plus 1 over CS, R, and we have LS plus R. Okay, now here is our next example. For the following circuit, we are asked certain things. Okay, so this is our circuit. The input is the voltage provided by this independent voltage source. the output is collected as the voltage drop across these two terminals. That's our V2. Okay, this is R1, this is 1 over SC1. The circuit is directly given in S domain. This is 1 over SC2, and here we have R2. Now for this circuit, okay, we are asked to find the driving point impedance Z in. Okay, so that's the impedance seen by the input, seen by this voltage source, Z in. And B, find the voltage transfer function, okay, V2 over V1, HV equals V2 of S over V1 of S, okay, so output over input. And C, locate the poles and zeros of the transfer function HV of S for R1 equals 10 kilo ohms, R2 equals 20 kilo ohms, and C1 is 100 nanofarads, and finally C2 given as 50 nanofarads. Okay, so once we have the transfer function in terms of R's and C's, we're going to plug in these numerical values, and for that we're going to figure out the poles and zeros of that rational function. Okay, let's proceed with the solution. Now, let's call this parallel connection of the resistor and capacitor as Z1, and let's call this series connection as Z2. So that's the equivalent impedance for this connection, and this is the equivalent impedance for this parallel connection. And then once we have Z1 and Z2, the input impedance, driving point impedance, simply is Z1 plus Z2, and the transfer function can simply be computed through voltage division, which is Z2 over the driving point impedance. Okay, so what Z1 is R1 in parallel with 1 over SC1, so that produces R1 times 1 over SC1 over R1 plus 1 over SC1, and that reads R1 over R1 C1S plus 1. Okay, as for Z2, we have 1 over SC2 plus R2, and that written as a single fraction reads R2 C2S plus 1 over C2S. Okay, so we have Z1 and Z2 now. So that produces the following driving point impedance. Zin equals Z1 plus Z2. Z1 is here, Z2 is here, and then that written as a single fraction produces the following, a little crowded expression: R1 C1 R2 C2 S square plus something times S, the first order term, plus 1, and that something is R1 C2 plus R1 C1 plus R2 C2. Okay, and as for the denominator, we have C2S times R1 C1S plus 1. So that's A, so that's our input impedance. Now let's move on to B. Okay, HV of S equals Z2 of S over Z in of S, because the transfer function is this voltage V2 over the input voltage V1, which can be computed, which means we're talking about a voltage division. Therefore, the ratio is Z2 divided by the overall impedance seen by the input. In other words, Z2 over Z in. And that reads the following: R2 C2 S plus 1, R1 C1 S plus 1, and we have R1 C1 R2 C2S square plus, okay, we're talking about that numerator, R1 C2 plus R1 C1 plus R2 C2S plus 1. Okay, so that's the transfer function. Now, the poles are the roots of the denominator polynomial, and the zeros are the roots of the numerator polynomial. The zeros are obvious where they are. Okay, we have minus 1 over R2C2. That's what for one of that's one of our zeros, and the other zero is at minus 1 over R1C1. Okay, to figure out the poles, let's use the numerical values. So that's part C. HV of S, the transfer function for this set of parameter values, reads the following: S plus 1 times 10 to the minus 3S plus 1 over 10 to the minus 6 S squared plus 2.5 times 10 to the minus 3S plus 1, which can be rewritten as S plus 1000 squared. So we multiply both numerator and denominator by 10 to the 6, and that produces S plus 1000 squared. And as for the denominator, we have S squared plus 2500 S plus 10 to the 6, which can be written as S plus 500 times S plus 2000. Okay, so that's our transfer function for the following numerical values. And then now it's clear where the poles and zeros are. The zeros are both are at minus 1000. As for the poles, we have one at minus 500 and the other is at minus 2000. And that completes the solution. The poles are at minus 2000 and zeros are at minus 1000 and minus 1000. Okay? Now, since we have two dynamic components here, two capacitors, so the degree of the circuit is 2, or order of the circuit is 2, and the order of the transfer function is also 2. That is, we have two poles, minus 500 and minus 2000. Therefore, that means these two real numbers, minus 500 and minus 2000, are the natural frequencies of our circuit. Okay, in our last example, let's consider a circuit with an op-amp, and under the assumption that the op-amp is in linear region, that circuit can be treated as an LTI circuit, and then once we have an LTI circuit, we can start talking about the transfer function. Okay, here is our circuit with the op-amp, which we'll assume is linear and also is in, excuse me, we're going to assume it's ideal, okay, infinite gain, and also we're going to assume that it's in linear region. This is our input, V1. And here we collect the output V2. R1, 1 over C1S, R2, and 1 over C2S. And the op-amp enters the picture in the following way. Minus, plus. Okay. Now, what we're asked is find the transfer function from input V1 to output V2. Find HV of S, the voltage transfer function. V2 of S over V1 of S. And for B, poles are located at, for the transfer, we're talking about the transfer function. So the poles of the transfer function are located at P1 equals minus 1000 radians per second, and the other pole at minus 5000 radians per second. When the resistances R1 and R2 are both 20 kilo ohms. Now, we're asked for this situation the capacitance values C1 and C2. Find C1 and C2. Okay, so it's a straightforward example. To simplify our analysis, again, we're going to define the shortcuts. Let's call this Z1, and let's call this the impedance Z2. Okay, Z1 is simply R1 plus 1 over SC1S, and Z2 is, we have to compute the equivalent parallel impedance. So here is the solution. Z2 equals R2 times 1 over C2S over R2 plus 1 over C2S. And that reads R2 over R2 C2S plus 1. Okay, and for Z1, we have simply R1 plus 1 over C1S, and that equals R1 C1S plus 1 over C1S. Now, let's obtain the transfer function. The op-amp is ideal, therefore there is no current entering from the negative terminal, okay, and also it's in linear region, otherwise we won't be able to talk about a transfer function, okay. It's in linear region, therefore V plus and V minus, they're the same. So that means this is same as ground, this node. So if you write KCL in that node, so this current is V1 over Z1, because the voltage here is the voltage here is 0, and this current is V2 over Z2. And since there's no current here, those two currents the sum of those two currents must be 0. Okay, so we have V1 over Z1 plus V2 over Z2 equals 0. And that immediately gives us the ratio V2 over V1. Okay, so HV of S, the transfer function, equals minus Z2 over Z1. Okay, and that equals, okay, Z2 is here and Z1 is also here. So after simplification, it reads R2 C1S over R2 C2S plus 1 times R1 C1S plus 1. So that's our transfer function. Okay. Now for B, so for B we're asked to figure out the capacitance values for the given resistance values, both at 20 kilo ohms, such that the poles are at minus 1000 radians per second and minus 5000. Now, in this expression, it's clear where the poles are in terms of R's and C's. One is at minus 1 over R1 C1, the other is at minus 1 over R2 C2. So we are given the R's, so it's therefore clear, it's easy to figure out the capacitance values. So P1 equals minus 1 over R1 C1. So that means minus 1000 equals minus 1 over 20 times 10 to the 3 times C1. Okay, which produces C1 equals 50 nanofarads. Okay, and likewise P2 equals minus 1 over R2 C2. So that means minus 5000 equals minus 1 over times C2, which produces C2 equals 10 nanofarads. Okay. Now, of course, we could have taken this to be P1 and this to be P2. In that case, the capacitance values would have reversed. That's also a possibility, which would produce the same poles for the transfer function. But in that case, the numerator will be different.